Hi guys, welcome to another video where we're going to look at another interesting mathematics problem to have a look at the problem solving process, how it works in practice, the kind of thought processes that you might need to go through to arrive at a solution to a challenging non-routine problem, let's say. Okay, so the problem that I've chosen for this video is from the book Further Pure Mathematics. I think I've used this in previous videos. Further Pure Mathematics by Bostock, Chandler and Rourke. It's a fairly old textbook from the early 80s, but packed with some really, really good, challenging problems if you really want to develop your problem solving skills and challenge yourself and really deepen your understanding and knowledge of mathematics. So the problem that we've got here is, it's from page 240 in my copy, question number 10, or problem number 10. And the problem is, show that the curve with polar equation r equals a plus b sec theta, where a is greater than b is greater than 0, has a loop. That's the first part. And then the second part is, prove that the area enclosed by this loop is given by this expression here. In many ways, there's a lot of routine aspects to this, so we will need to do some integration. We're kind of anticipating that. But nevertheless, we still need to understand some of the terminology that's involved. We need to understand what it means for a curve, for this to be the polar equation of a curve, so it potentially needs to be familiar with polar coordinates. And we need to know what it means by a loop. And how we're going to actually identify the presence of a loop on this curve, because we're not given a picture of the curve. And this is often the case in a lot of problems. You're asked to comment on certain features of a curve without actually knowing what the curve looks like. And this is perfectly normal within mathematics when we've got certain analytical algebraic techniques that we can use instead to discover, to find out certain bits of information about a curve when we don't even know what the curve looks like. So one way that we could try to figure out, try to prove, I guess, that this the curve that represents this equation has a loop is to try to draw its graph. Try to actually draw the graph of this equation. Obviously, in this day and age, it's as opposed to the early 80s, you can just go on maybe Desmos or something like that, and you might be able to get a picture of the curve straight away. But this is not really satisfactory. We really need analytical techniques, and actually knowing what the curve looks like in this case is kind of putting the cart before the horse. For the simple reason that for us to draw the curve the curve that represents this equation, we would already need to know that there is a loop there. But we need to find out that there's, so that even if we arrive at a satisfactory picture of the curve, we need to know what we're hoping to find out from that graph. We already need to know in order to draw the graph. So it's kind of, this is what I mean about it's kind of putting the cart before the horse. So we need to know, when we're dealing with polar coordinates, what do we mean by a loop, and how can we identify the presence of a loop? So a loop, when we're dealing with polar coordinates, of course, r is the distance from the pole, and theta is the angle made with the initial line in a anti-clockwise direction. So I still tend to think in terms of quadrants, even when I'm dealing with polar coordinates, but generally speaking, we've got the initial line here, which represents theta equals 0. And I will still think in terms of the usual four quadrants, but instead of an x-axis and a y-axis, we've now got this line represents theta equals pi by 2. This is theta equals pi, and this is theta equals 3 pi by 2. Obviously, we're working in radians here rather than degrees. If you're not familiar with radians, then it's really essentially you get to grips with radians in order to deal effectively with polar coordinates, especially when you're going to be dealing with integration and differentiation and things like that. So a loop is going to occur when, let's say in this particular case, we've got a plus b, r equals a plus b sec theta. Well, if r, the distance from the pole, which is here, is 0 for at least two distinct values of theta, then we've got a loop. Because what's going to happen is, for one value of theta, we're going to be at the pole, and then we're gradually going to, I'm just going to draw, this is not necessarily what the graph of this looks like, but just to give an example, we're going to kind of move away from the pole, and then for another value of theta, we're going to come back. So it might be that there's two values of theta, for which r is equal to 0, in which case we get one loop, or there might be more than there might be more values of theta, in which case you're going to get potentially multiple loops. So we're told here to show that the curve r equals a plus b sec theta has a loop. Does this rule out the possibility that there might be more than one loop? Not necessarily, but it will be easy for us to see that there is only going to be one loop anyway. But we're going to do this without trying to draw the graph of this. What we're going to do instead is we're just going to solve this equation. This will be better. There we go. Okay. So we need to solve the equation a plus b sec theta is equal to 0. So when is a plus b sec theta going to be equal to 0? Well, it's going to be when sec theta is equal to minus a over b, or equivalently when cos theta is equal to minus b over a, or equivalently one possible value is going to be when theta is equal to inverse cos minus b over a. Can we guarantee that there's actually going to be a solution here? Yes, we can. All we've got to do is think about the graph of sec. So the graph of sec looks something like this. So this is pi by 2, where we've got this vertical asymptote. That's pi. We've got 1 there. We've got a local maximum here at minus 1. But the information that we're given is that a is greater than b is greater than 0. So if a is greater than b is greater than 0, that means that a over b is going to be greater than 1. So minus a over b is going to be less than minus 1. Why is that important? Because that means that minus a over b is going to be over here somewhere, or down here below minus 1. And we can see from the graph, therefore, that we're going to get two solutions to our equation. And it's these two solutions which are going to tell us that we've got a loop on the curve of r equals a plus b sec theta. So one of these solutions, this one here, is going to be theta equals inverse cos minus b over a. The other one, by symmetry of the graph of sec, is going to be at inverse cos, 2 pi minus inverse cos minus b over a. Okay, so that tells us that there's a loop. There's one loop in the curve, r equals a plus b sec theta. So that's the first bit done. With the two values being inverse cos minus b over a and 2 pi minus inverse cos minus b over a. The reason I've got to do this, 2 pi minus inverse cos minus b over a, is because inverse cos the inverse cos function is only valid between 0 and pi. It's only valid, it will only return values between 0 and pi. So this other solution, which is further on, I've got to do a little bit more work. I've got to use the symmetries of the graphs to figure out what the specific value of that is going to be. So there are two values: inverse cos of minus b over a, and this one actually I'm not going to bother too much about. It's this one that we're going to be interested in. So both of these values we've got r is equal to 0, and therefore we've got a loop. And also we can see if we continue the graph of sec up to 2 pi, there's not going to be any other values where sec theta is going to be equal to minus a over b. So there's definitely only one loop. Okay, so the next thing that we need to figure out is what is the area, or, well, we know what we're aiming for, but we need to find the area enclosed by that loop. Okay, and by symmetry, what we can see is that the area, if I were to draw a quick graph again of what this might look like, so for some value of theta, inverse cos minus b over a, r is equal to 0, and then we kind of get something that looks maybe like this. But it's not very well drawn here, but these are going to be symmetrical. So this bit above the line theta equals pi is going to be equal in area to the bit below the line theta equals pi, even though it doesn't look like it from the way I've drawn it. They're going to be the same. So all I need to do is find the area, this area from inverse cos minus b over a to pi, and then double that area, and that will give me the total area here. Okay, so because we're dealing with polar coordinates, we need to make sure that we integrate correctly. And the formula that we need to use for integrating polar coordinates is half r squared d theta. And then we've got our limits. Our limits are going to be, in this case, inverse cos minus b over a to pi. But remember, that only figures out half the area that we're looking for. The full area is going to be twice that. So this is going to be equal to the integral of r squared d theta from inverse cos minus b over a to pi. Wait a minute. This is, excuse me, a damn fine cup of coffee. Okay, so this is equal to r squared, sorry, the integral from inverse cos minus b over a to pi of r squared, which is a plus b sec theta all squared, which is going to be a squared plus twice ab sec theta plus b squared sec squared theta d theta. This is just a fairly routine integral at this stage, in all honesty. There's nothing particularly difficult about what's going on here. So what do we get? Remember, we're integrating with respect to theta here. So it's going to be a squared theta plus 2ab. Now, this one I always forget, the integral of sec theta, but I know how to figure it out. It's sec theta is equal to, so the integral of sec theta is going to be the integral of sec theta. So if I multiply numerator and denominator by sec theta plus tan theta over sec theta plus tan theta, then this the numerator here is the exact derivative of the denominator, and therefore this is going to be the natural logarithm of the modulus of sec theta plus tan theta. So this is 2ab natural logarithm modulus sec theta plus tan theta plus b squared integral of sec squared theta is tan theta, and got our limits inverse cos minus b over a and pi. Okay, let's get rid of this. I think I need some new board rubbers. So, plug in the values. We get a squared pi plus twice ab natural logarithm of the modulus of sec pi is -1, tan pi is 0, plus b squared tan pi is 0, minus, I'm going to have to go on to another line, a squared inverse cos minus b over a plus twice ab natural logarithm modulus of, so sec of inverse cos minus b over a is going to be 1 over cos of inverse cos minus b over a, which is a over minus a over b. Tan theta, okay, I'm going to have to do a little bit of work to figure this out. So if this is a right angled triangle, let's just take our angle to be, what shall I use, x. And let's just assume that x is acute for the time being. But if we've got cos x equals b over a, then we've got something like this, and therefore the length of this is going to be the square root of a squared minus b squared. So that means that tan x is going to be equal to the square root of a squared minus b squared over b. But because we know that this angle corresponding to inverse cos minus b over a is going to be obtuse, that means that tan of the angle that we're interested in is going to be minus square root of a squared minus b squared over b. So we're going to have here plus, so it's going to be minus the square root of a squared minus b squared over b plus b squared square root of a squared minus b squared over b. So there's a load of cancelling out here. So we've got the a squared pi. Now, initially I was a bit worried about this because I thought, a squared pi doesn't appear up here, but there is something else that we need to do, which if you've been keeping your eyes peeled, you'll have seen what it is. 2ab natural logarithm of the modulus of -1 plus 0 is just natural logarithm of 1, which is 0. B squared times 0 is 0. Minus a squared inverse cos minus b over a minus 2ab natural logarithm of, because this is modulus, I can get rid of the minus signs, and I can get rid of the modulus sign as well, for that matter. And I'm just left with a plus the square root of a squared minus b squared over b, plus this b cancels with one of the b's there to give b square root of a squared minus b squared. Now I've just got this to worry about. So, but this is easily dealt with. Because if I think about the graph of cos, the solution that I'm interested in is here, which is inverse cos minus b over a. Well, this is just going to be kind of the negative of this solution here, this value, which is going to be inverse cos of b over a. Okay, so this value here is just going to be equal to, using the symmetries of cos, is just going to be pi minus inverse cos of minus b over a. Well, that's what I've got here. If I take the a squared out as a common factor, I'm going to have a squared pi minus inverse cos minus b over a with all of the rest. Replace the pi minus inverse cos minus b over a with just cos inverse b over a. And that will give me the value that I'm looking for the area. And that is a complete solution to this problem.